for Hadoop developers in India. 80% of market employers are looking for big data experts from engineering and management domains. Now with this, let us move ahead and discuss about the top companies that are hiring Hadoop developers. The top companies which are hiring Hadoop developers are Oracle, Dell, Capgemini, IBM, Mphasis, CGI, Facebook, Twitter, LinkedIn, Yahoo, Medium, Adobe, Infosys, Cognizant, Accenture, Oracle, Dell, Amazon, and many more. Now, let us move ahead and understand the roles and responsibilities of a Hadoop developer. Different companies have different issues with their data. So, the roles and responsibilities of the developers need to be a varied skill set to be capable enough to handle multiple situations with instantaneous solutions. Some of the major and general roles of a Hadoop developer are as follows. Firstly, you should be capable enough to develop Hadoop and implement it with optimum performance. Followed by that, you should be able to load data from different data sources, which might be RDBMS, DBMS, data warehouse, and many more. Followed by that, you should be capable enough to design, build, install, configure, and support Hadoop system. Followed by that, you should be able to translate complex technical requirements in a detailed design. You should be able to analyze vast data storages and uncover insights. You should be also able to maintain security and data privacy. You should be capable to design scalable and high-performance web services using data tracking. High-speed data querying is a must. You should also be able to load, deploy, and manage data in HBase. Defining job flows using schedulers like Zookeeper is mandatory. And finally, cluster coordination services through Zookeeper is also important. Now with this, let us also discuss about the future of Hadoop developers. Major large-scale enterprises need Hadoop for storing, processing, and analyzing their big data. The amount of data is increasing exponentially, and so is the need for this software. In the year 2018, the global big data and business analytics market was standing at $169 billion US, and by 2022, it is predicted to grow to $274 billion US. However, a PwC report predicts that by 2020, there will be around 2.7 million job postings in data science and analytics in the US alone. If you're thinking to learn Hadoop, then it's the perfect time. The prerequisites to install Hadoop in Windows operating system are Java. So, we all know that Hadoop supports only Java version 8. So firstly, we need to download Java 8 version. Followed by that, a latest Hadoop version, which we need for our operating system, then the configuration files. So these were the prerequisites. Now let's quickly go ahead and download Java 8 version into our local system and also Hadoop. So you can see that this particular web page belongs to Oracle, and here you'll be getting your Java Development Kit number 8. So these are the various versions available for Java 8 for Linux as well as Windows. So we need a JDK which is compatible with Windows. So here you can see that Windows x64 JDK version which will support Windows. So this particular link will redirect you and download JDK 8 for you into your local system. Once you click on it, it will ask you to accept the license terms from Oracle. Now you can just click on download. Followed by this, you will be redirected into a login page where you need to create your own account with Oracle so that you can download this JDK. Don't worry, this account is free of cost. So you can see the JDK is getting downloaded here. So as the JDK is getting downloaded, we shall now move ahead and download Hadoop for our local system. So this particular web page belongs to Apache organization where we can download Hadoop for free. So these are the various versions available for Hadoop, which are 2.10, 3.1.3, 3.2.1, and many more. So we shall select the latest version of Hadoop. But while you're selecting the latest version of Hadoop, please make sure that you're not actually downloading the exact latest version of Hadoop. Here, you can see we have 3 different versions, 3.1.3, 3.2.1, 3.1.2. As you can see, 3.2.1 is the latest version. We have to select the version which is earlier to it, which is 3.1.3, because this particular version will be the stable version. Now we shall move ahead and select binary. Once you select binary, you will be redirected into a new web page where you will have a mirror link. Select that mirror link and your Hadoop will be downloaded for your local system. As you can see, Hadoop 3.1.3 tar.gz is getting downloaded. Now here you can see I have successfully downloaded Hadoop version 3.1.3 tar file as well as JDK 8, and those two files are successfully moved into my C drive. Now let's install Java first. Now make sure that you create a new folder for Java. So select change, and here select Windows C drive, then select make new folder. Now rename this new folder as Java, click OK. And now select next. You can see the installation procedure has now been started. You can see Java Development Kit 8 has been successfully installed. Now we shall enter into program files and move our JDK into Java file, because sometimes there will be an error while we set environment variables for Java. So you can see inside program files we have another folder called Java. So inside Java, there you have our JDK. So now what I'll be doing is just moving this JDK into Java file which we have created in C drive, this one. Now you can just delete this Java file from your program files so that you don't have to mess with duplication of Java file. Now you have your Java and JDK in one single file, which is Java, that is you have created in Windows C drive. Now we shall move ahead and set the environment variables for Java. So click Windows and then enter into settings, and inside the settings select system, and inside system just type in environment variables. And there you go. Select the edit the system environment variables option, and you have this dialog box. Here select environment variables, and inside the environment variables you need to set the Java home as well as path for Java. Now select new, and here just type in Java home, and here let us add the location of JDK bin. So here we will add in the variable value, that is the JDK bin location. So our JDK bin location is in the C drive, and inside the C drive we have the Java folder, and inside Java folder we have our JDK 1.8.0, and inside JDK file we have the bin location. So this will be the home location for Java. Select OK, and then now move into the next dialog box, which is the system variables, and inside that select path and select edit. Here create a new path variable which will be the JDK path, the same location, that is the bin of JDK. Select OK, and now select OK again, and now OK, and close it. Now Java has been successfully installed into our local system. Now let's check Java is functional or not. We can do that by selecting Windows R, and inside Windows R just type in cmd so that you can open your command prompt. Here just type in Java C. If you see the set of files popping up into your terminal, then it means that Java is working properly. So you can see Java is working just fine. Now let us check the version of our Java installed into our local system. So this can be checked by typing in Java space hyphen version. So you can see we have 1.8 version which is running in our local system. Now that we have successfully installed Java into our local system, let us now move ahead and install Hadoop into our local system. You can see that we have downloaded the tar version of Hadoop. So for that, we need to extract it first. Now you can see that the process of extraction has been completely finished, that is 100%, but you have 3 errors. You can ignore these errors. Now just close the extracting process. Then you have your Hadoop file. Now let us rename our Hadoop 3.1.3 as just Hadoop to reduce the confusion. Now that we have successfully extracted Hadoop, let's set environment variables for Hadoop. But before that, let's set the configuration of Hadoop. You can select Hadoop, and inside that you have a file called etc. And inside etc, you have another folder with the name Hadoop. And inside that, you have a set of folders. So out of these all folders, we have 4 important folders. They are core site.xml, then hdfs site.xml, followed by hdfs. We have another one which is mapped site.xml, and lastly the yarn site.xml file. So we need to edit all these 4 different files. And once after we edit these 4 files, we need to edit one last file, which is the Hadoop env Windows command prompt file. So here we're just going to add in the Java home location. Now let's quickly edit all those 4 files. So we have successfully opened our 4 important files, which are core site.xml, mapreduce site.xml, yarn site.xml, hdfs site.xml, followed by the 4 important files. The last file, which is the Hadoop environment.cmd file. Here we are going to set this Java home location. Now let's first set the values for core site.xml. So the values that are changed in core site.xml are the properties. So inside the configuration, I have added one property, which is the file location, that is fs.default file system, and the local host location, that is 9000. Now let us save this core site.xml. Similarly, we need to also edit mapreduce site.xml files. Here, inside this, we need to add some properties. As you can see, we have also edited the configuration files of mapreduce site.xml. Let's save it. Now followed by the mapreduce site.xml, we have yarn site.xml. Let's edit this also. As you can see, the yarn site.xml is also being updated. Don't worry about this property file. I will link this in the description box below. You can have the access to it and you can use the same configuration file and install Hadoop. Followed by yarn site.xml, we have the last one, which is hdfs site.xml. But before editing this particular file, I want you to create a new folder in Hadoop location, which is data. Let's see how to create it. So this particular folder is inside C drive. This is Hadoop, and inside this Hadoop file, you need to create a new folder with the name data. Inside data, you need to create 2 more new files, which are data node and name node. So the first folder will be name node, and now another folder, which will be our data node. So now let's copy the location of data node and name node. So this location is the data node location, and followed by that the name node location. So this particular location will be the name node location. We have the 2 locations copied onto our clipboard. Now let's go back to the hdfs site.xml file and edit the configurations here. So you can see that we have edited the configuration file of hdfs site.xml, and inside the configuration, we have provided the replication factor, which is the first property, and we have set the value as 1. Since we're using our local system, we might want to save memory, so the replication is only 1, but the default value for the Hadoop replication factor is 3. And followed by the first property, the second property, which is our name node. So we have provided our name node location, which is Hadoop file, and followed by that the data file, and inside that we have the name node. And similarly, the last property, which is the data node property. So here the value is Hadoop data node. Now let's save it. Now that we have successfully edited all our 4 important files, let's get back to Hadoop env.cmd file and edit the Java home location. So for safer side, let's get back to environment variables and get our JDK location. So this particular location is the location for Java home. We might want to remove the bin over here. So only C Java JDK is enough to set the Java home into our Hadoop env.cmd file. Now let's save this particular file and close it. So all the important files have been now successfully edited. Now let's go back to environment variables and set home and path for Hadoop. Now select new and write in Hadoop home. So this particular location, that is C Hadoop bin, is the location for Hadoop home. Now select OK. Now let's get back to path and set path for Hadoop files. In here, let's set up a new path variable, that is Hadoop bin. And now remember to create another path variable, that is your sbin. So to locate sbin, get back into Hadoop and select sbin, and this will be the location or path value for your sbin. Select that and edit a new variable in path and paste it. So that's how you set sbin, and select OK, OK, and finally another OK, and close the system properties. Now that we have successfully set home and path for Hadoop, let's go ahead and fix the configuration files. You can see that inside the bin folder of Hadoop, we are missing some important configuration files. To fix this, we need a new configuration file, which will be available in the description box below. You can click on that particular link and the required configuration file will be downloaded into your local system. And all you need to do is just replace that particular file with your bin folder in your Hadoop. You can see that there is a new file in my Hadoop, which is Hadoop configuration fixbin1.rar. Now, all you need to do is just extract this particular folder. You can see that the folder has been successfully extracted and all the executable files that you require in your Hadoop have been downloaded successfully. Now, what you need to do is just move this bin into your Hadoop bin. So cut this bin and get back to Hadoop and enter bin. So just delete this particular bin and replace it with a new one. So there you go, you have successfully done it. Now let's delete the unnecessary files. There you go, as good as new. So you have all the executable files and your Hadoop has been set. To check if Hadoop is functioning properly or not, let's open CMD and type in hdfs space name node space hyphen format. If you see a set of files popping up on your terminal, that means you have successfully installed Hadoop. You can see that the name node has been successfully getting started. Now let's open a new terminal and start all the Hadoop daemons. Here, you just need to enter your Hadoop location file, that is cd space Hadoop. Now you are inside Hadoop and inside Hadoop enter sbin. Now you're inside sbin. Now you need to type in startall.shr, startall.cmd. And there you go. All your daemons are getting started. So that's how you install Hadoop into your local Windows operating system with the version Windows 10.
Now you'd be thinking, how does SDFS work? First of all, as you know, SDFS stands for Hadoop Distributed File System. So let us take a step back and understand what actually is a distributed file system in the first place. A distributed file system talks about managing data, that is files or folders, across multiple nodes or computers. It serves the same purpose as the file system provided by the OS in your PC. For example, for Windows, you have something called as NTFS, or for Mac, you have something called as HFS. The only difference between the file system that is there in your PC, that is your local file system, and a distributed file system is that instead of storing data in a single machine, in case of distributed file system, your data is stored in a cluster, which is again nothing but a bunch of computers connected to each other forming a network. Even though the files are stored across a cluster, the DFS will organize and display your data in such a manner that if you try to access the data from any one of the machine in the cluster, you will feel as if the data is stored in the machine that you are using. In other words, DFS provides you an abstraction of a single big machine that has a combined disk capacity equal to sum total of disk capacity of each node in the DFS cluster. Now let me give you an example just to clarify things further. Suppose you have a DFS comprising of 4 computers where each computer has a disk capacity of 1 TB. In this case, the DFS will provide you an abstraction of a very big machine that has combined storage of 4 TB. Now you can go ahead and store a single file of, let's say, 3 TB, which will eventually get stored and distributed across the 4 computers. So this is all about DFS, guys. Next, you may ask why we need DFS in the first place. I mean, we could have just increased the disk capacity of single machine to whatever that is required. Well, first thing is, there is a limit up to which you can increase the disk capacity of a single machine. Even if you somehow manage to store all of the data on a single machine, it would lead to another big problem. That is, it would take a lot of time to process the data using a single machine. Let us take an example to understand this. For example, let us say I'm having a 4 GB file that takes 4 hours to completely process it using a single PC. Now what I did, I used DFS and stored the same 4 GB file in a 4 node cluster, where each node was storing a chunk of file that will be equal to 1 GB. So therefore, in total, the 4 GB file was distributed across the cluster. Now what I can do, I can process each chunk of file parallelly using the 4 computers, thus reducing the entire processing time, which will be reduced to 1/4 of the former, that is equal to 1 hour. So that is the advantage that you get with DFS. So I guess by now you would have understood what is DFS or why do we need it. Let us come back to SDFS again. So again, SDFS is also a distributed file system, but for Hadoop, that allows you to store huge data sets, that is terabytes and petabytes of data, across the cluster or multiple machines, so that you can go ahead and process the data stored in each machine in parallel. Simple yet quite powerful idea, isn't it? So that is the main reason why Hadoop or SDFS became so famous. Now, the next question that would be pondering in your mind is, how does SDFS manages the data? Or who distributes the data across the cluster? How can one access the data present inside SDFS? To answer these questions, you need to understand the architecture of SDFS. Now, SDFS or Hadoop cluster follows master-slave topology. It means that you have one master node and remaining all other nodes are slave nodes. In SDFS, the master node is called as name node, whereas the slave nodes are called as data nodes. Now, data nodes are actually responsible for storing the actual data, whereas name node, being the master node, is responsible for managing all the slave nodes or data nodes. Other responsibility of name node includes maintaining and managing metadata. The metadata is information about data that is there or present inside the data nodes. So name node will be keeping all those information regarding which data are stored in which of the data nodes. Along with that, data node are supposed to send some heartbeat or a signal so as to ensure that all the data nodes are working to name node. So if, let's say, one of the data nodes stops sending that signal, the name node will assume that that particular data node has been failed, and that same will be notified to the admin so that a new data node can be permissioned. So other information in the metadata are like file permission, directory permission, the data locations, and all that. So all those stuffs are there in the name node metadata. So now that you have understood the architecture that is followed by SDFS, where we have one master node and we have slave nodes as data nodes, now the question is how files are actually stored inside SDFS. Just like any file system, in case of SDFS also, the files are stored as blocks. The only difference between the file system block size that is there in your system to that of our SDFS is the default size of each block in SDFS is 128 MB, since we are dealing with a large or huge amount of data set. It is configurable and you can go ahead and change the default block size as per your use case. Now let's understand how does this work. For example, let's say I want to put a file of 380 MB into SDFS. So this 380 MB file will be broken down into 3 data blocks, where the first 2 data blocks will be of 128 MB, thus making 256 MB, and the last block will be occupying 380 minus 256 MB, that is equal to 124 MB. Then finally, these data blocks will be distributed across the cluster, that is in different data nodes. Now, when you will look at this implementation, you will find one more problem. What will happen if one of the data nodes containing the data blocks crashes? So how will name node ensure, or how will SDFS ensure fault tolerance with respect to the current implementation that we are having? Let's understand this problem with an example. So we'll take the same example that we were having in the previous case, where we are having one file of 380 MB that has been distributed across the SDFS with 3 blocks. Now let's say the third data node having the 124 MB block has been crashed. So in this case, we will not be able to retrieve the data, or we will be facing data loss issue. So SDFS has a solution for it called as replication factor. So what happens is whenever you are storing any data or copying any file into SDFS, it is broken down into blocks, and each blocks are replicated thrice by default and are distributed across the data nodes. In case if any of the data nodes fails, in that case, we can again retrieve the data by having a replica that will be stored in some other data nodes. So that is how your SDFS ensures fault tolerance capability. Also, there is one more advantage of having master-slave topology is that we can go ahead and add more nodes on the fly. So for example, let's say I want more disk space in my cluster. In that case, what I can do, I can commission new data nodes on the fly without affecting the current infrastructure. So enough of the theory, guys. So let's go ahead and have a look at the real cluster. How does it look like? And what are the different ways via which we can go ahead and access SDFS? So these are edge node, guys. Let me log in. All right. So basically, we'll be having 2 types of file system over here. One will be the local file system with respect to your edge node, where all the files will be there. And then there will be distributed file system with respect to SDFS. So let me list all the files and directory in both the cases. For example, for local file system, I will be using local shell command, which is ls. And using that, you can see these are the files that is there inside my edge node. Now for listing out the directories and the files that is there inside my SDFS, I will be using SDFS shell command. So for that, you have to go ahead with SDFS DFS, then -ls, and then you provide the name of the directory on which you want to list the files or subdirectories. For example, in my case, I'll be looking at my profile directory, that is /user/edu_bigdata user. So as you can see, these are the files and directories inside my profile directory. So now you would be understanding how SDFS provides you that abstraction that you are using a single big machine. So let's go ahead and do some demos as well. For example, let's say I want to create a directory inside my DFS. So for that, I'm going to go ahead and say SDFS DFS hyphen make dir, and we'll go ahead with the name of the directory, which will be user slash edu big data user. And let's name the directory as SDFS dir. All right, so the directory has been created. Let's go ahead and list all the files that is there inside SDFS again. For that, again, I'm going to go ahead and say slash user slash edu big data slash user. Oops, I made a mistake, sorry. So here you can see I'm having a subdirectory called as SDFS dir, which has been created recently. All right, now let's go ahead and copy some of the data from edge node to SDFS. So if I do ls, these are the files that is there inside my edge node. Let me choose one file. So basically I'll be copying this particular tar file. So let me check the size of this tar file. All right, the file size is of 1.1 GB. Let's go ahead and copy it into the cluster. So I'll say SDFS DFS hyphen put. Put is for moving data from your local system to SDFS. And then I'll mention the name of the file, which is cdh hyphen char dot tar.gz, and then I'll mention the directory where I want to copy it inside SDFS. So which will be slash user slash edu big data user slash SDFS underscore dir, the directory that we have created recently. Now let's go ahead and list the files that is there inside the newly created directory so as to ensure whether the copy has been done successfully or not. For that, I'm going to again do SDFS DFS hyphen ls. Then we'll mention the directory path. So let me copy it and paste it over here. So as you can see, found one item, that is the file that we have copied recently. Now let us go ahead and check the number of blocks that has been made with respect to this particular file that we have copied inside SDFS. So I'm going to say Hadoop fsck, and then again I'm going to mention the directory path. So as you can see, we have total of 9 blocks that has been created with respect to 1.1 GB file, and each block has been replicated thrice by default. So in total of there will be 27 blocks there residing in SDFS in different data nodes. So this is how your SDFS works, guys. Now for a programmer, again, I don't have to worry about how data blocks are being created or how it is being distributed among different nodes. All I have to worry about is the logic that I'll be working on these data. So that's why your SDFS provides you all those abstraction and provides you tools and all those APIs so that it is very easier for you to go ahead and access it and manage the data that is there inside SDFS. With the given fact that even if I run a job or even if I process the data, that again the data will be processed locally in the each node in a distributed and parallel fashion. Thus, we'll be getting a reduced processing time. So whenever you're talking about huge amount of data sets or huge data sets, SDFS is the best option. The last fact that I'm going to mention is that all these SDFS hardwares are commodity hardware. So basically, Hadoop is a very cost-effective solution to big data problem. In case if you have a specific use case that requires more cluster configuration, then you can go ahead and upgrade your cluster or hardware on the fly. You can add more nodes to it so that more parallelism can happen and you can again process a large data sets.
What is Hadoop MapReduce and why is it required? So Hadoop MapReduce is actually the processing unit of Hadoop, using which you can process the big data that is present on Hadoop HDFS or that is stored on Hadoop HDFS. But what is the requirement? Why do we need Hadoop MapReduce in the first place? It is because the big data that is stored on Hadoop HDFS is not stored in a traditional fashion. The data gets divided into chunks of data which is stored in respective data nodes. Okay, so there is no complete data that is present in one single location or one centralized location. Hence, a native client application which used to be there like a Java application or any other application cannot process that data right away. And hence we needed a special framework that has the capability of processing the data that stays as a blocks of data into respective data nodes, and the processing can go there and process that data and then only bring back the result. So that kind of a framework is Hadoop MapReduce. And we'll move on to the next slide and we'll see MapReduce in a nutshell. So this particular slide basically gives you the overview of MapReduce and what are the things that are related to MapReduce. To start with, What are the applications of MapReduce or where it is used? For example, it is used for indexing and searching. It is used to create classifiers. It can be used to create recommendation engines, like it has been created by big e-commerce companies like Amazon, Flipkart. It can be used for analytics by several companies. When we talk about the features of MapReduce, it is a programming model. It can be used for large-scale distributed model like Hadoop HDFS. It has the capability of parallel programming, which makes it very useful. When I talk about functions that are present in MapReduce, there are basically two functions that get executed. One is the map function and the second is the reduce function. If you talk about design patterns that has already been there in the industry for a long time, yes, you can also implement all those design patterns using MapReduce like summarization, classification, recommendation, or analytics, right? Like join and selection. MapReduce has been implemented by major giants like Google, and it has also been adopted by Apache Hadoop for HDFS, for processing data in HDFS, for processing data using Pig, for processing data using Hive, or for storing data or executing queries over the big data using HBase, which is a NoSQL database, right? So this is something which actually gives you the overview of MapReduce and what are the various features, what are the applications, where it is implemented, what are the functions that are used. That kind of information is given in this slide. Guys, are you able to grab that information? And now we'll explore the two biggest advantages of MapReduce. The very first advantage is parallel processing. You must be aware of parallel processing from before as well, because it's not a very new term. Using MapReduce, you can always process your data in parallel. Okay, as you can see in the diagram, there are 5 slave machines, and there's some data that is residing on these machines. These boxes are nothing but representing a chunk of data, a block of data, or a HDFS block, which is getting processed in the respective slave machines, right? You can see a circle going on. So this simply represents the processing. Okay, so in here data gets processed parallelly using Hadoop MapReduce, and hence the processing becomes fast. So it is as simple as the work time problem that you would have solved in your school days. For example, you would have solved a problem like, if a particular task is done by one person, he is going to take 1 day. So the same task, if it is done by 3 persons, how many days it is going to take to finish the job, right? So what are we doing there? We are actually distributing the task among 3 people, and hence the time that is taken to execute that job becomes less, right? Similarly, same happens in Hadoop MapReduce. What happens is entire chunk of data gets divided by Hadoop HDFS into HDFS blocks, and the processing now processes this data in parallel, and hence the processing becomes fast. So I'll move on to the next slide, and we'll explore the second advantage of Hadoop MapReduce, that is data locality. This is one versatile thing that is given by Hadoop MapReduce, that is, you're able to process the data where it is. What does it mean? Let me tell you. The data that you move into Hadoop cluster gets divided into HDFS blocks, and these blocks are stored in the slave machines or the data nodes, right? As you can see, the data is stored in all these slave machines that are there in this picture, right? What MapReduce does is, it sends the processing, it sends the logic to the respective slave nodes or the respective data nodes where the data is actually residing as HDFS blocks. So what happens is, the processing is executed over a smaller chunk of data in multiple locations in parallel, right? This saves a lot of time, as well as it saves the network bandwidth that is required to move big data from one location to other. Just remember that this was big data which was broken down into chunks, right? If you start moving that big data through your network channels into a centralized machine and then process it, it will give you no advantage, right? Because you're going to consume the entire bandwidth just in moving the data to a centralized server, right? So using MapReduce, you are not just doing parallel processing. However, you're also moving the processing, the logic that you would like to execute over big data into the respective slave nodes where the chunks of data are present, and hence you're also saving a lot of network bandwidth, right? Which is very beneficial. Finally, when the slave machines are done with the processing of the data that is stored at the slave machines, they send back the results to the master machine. Because the results are not as big as the blocks that were stored on the slave machine, hence it will not be utilizing a lot of bandwidth, right? So what they do is, they send the results back to the master machine. These results are aggregated together, and the final result is sent back to the client machine, which actually submitted the job. So we'll move on to the next slide, and we'll explore the traditional versus the MapReduce way. For this, we'll take a real life analogy of election votes counting. Okay, everyone would be aware of elections, right? It happens everywhere. So you would be aware of booths as well. So booths are the location where people come and cast their votes, right? So there are n number of booths spread across the country, right? Let's take a scenario where we have 5 booths, okay, where people will go and cast their votes. Now, we also have a result center which has all the information of the booths that are there and where they are located, okay. However, when people come and cast their votes in these respective booths, the votes are kept there itself. That is, booth A will have its own n number of votes, booth B will have n number of votes, booth C will have n number of votes. Similarly, booth D and E will also have n number of votes that were casted there itself. That information is not shared with the result center, right? So let's move on and let's see how does the vote counting will happen in the traditional fashion. Okay, so if you solve this problem using the traditional way, all these votes will be moved to a centralized result center right here, and then the counting would start. Now in this case, if we do this, what happens is we need to move all the votes to a result center, which is a costly affair, right? That is, you'll have to gather all the votes and move to a center location. So there is a cost involved along with that, along with the effort, right? Second point is result center also gets overburdened because it has to count all the votes that were casted in these respective booths, right? As well as since they are counting votes that were casted in all the booths, it is going to take a long time. So this process doesn't work very well. Let's see how does MapReduce solve this problem. So the very first thing is MapReduce doesn't follow this approach. Now when you see the MapReduce way, what happens is, as you already learned in our previous slide, that is MapReduce follows data locality, right? So that means it is not going to bring all the votes into a centralized result center. Instead, it will do the counting in the respective booths itself in parallel, right? So what is happening is, so once the votes that are casted on every booth are counted, they are sent back to the result center, and the result center now only has to aggregate the results that were sent from respective booths and announce the winner. So this way declaring the result becomes easy and very quick. Otherwise, I'll move on to the next slide. Okay, let's move on. Now let's understand MapReduce in detail. Okay. Now what did we do in the previous example? So we had an input, okay, and that input was distributed among various booths. Now every input was processed by a respective map function, okay. In the starting I told you that MapReduce has got two functions, one is map and the other is reduce. So the counting part that I talked about, which was done on the respective booths, was done by the map function. So every input at every booth was counted using the map function right here. After that, the results were sent to the reduce function. So the aggregation part is done by the reduce function and the final result is given as the output. So this is what has happened in our previous example. Okay, so the entire thing can be divided into map task and reduce task. Map task gets an input, the output of the map task is given to the reduce task, and this reduce task gives the output finally to the client. In this slide, we'll understand the anatomy of MapReduce. So what happens is a MapReduce task works on a key value pair, as you can see on the left. So when I talk about a map takes the input as key value, okay, and gives an output as a list of key value, okay. Now this list of key value goes through a shuffle phase and an input of key and a list of values given to the reducer. Finally, the reducer gives you a list of key value pairs. Okay, in this slide, what you need to understand is MapReduce works with key values itself, and the remaining thing we'll be understanding this in the coming slides. We'll move on to the next slide. Now let us take an example to understand the MapReduce way. Okay, so we had an input, right? The input that you have gets divided or it gets splitted into various inputs. Okay, so that process is called input splitting. So the entire input gets divided into splits of data on the basis of the new line character. The very first line is the first input, that is deer, beer and river. The second line is the second input, car, car and river. Okay, it would be deer, car and beer. Now let's move on to the next phase, that is the mapping phase. Now in the mapping phase, if you can see, what we do is we create a list of key value pairs. Okay, so the input is key and value. So key is nothing but the offset of the line number. The line number is the key and the entire line is the value. Okay, so line 1, the offset would be the key and the value would be deer, beer and river. In real life, the line number or the offset is actually a hexadecimal number. However, to make it easy, we will only consider it as 1 or 2, right? So line number 1 would be the key and the entire line would be value. Okay, when it is passed to the mapping function, what mapping function will do is it will create the list of key value pairs. For example, deer. So what it will do is it will read every word from the line and it will mark 1 after the comma. Okay, it will mark 1 as a value. So deer comma 1, beer comma 1 and river comma 1. Why are we putting 1 after every word? It is because deer is 1 count, so deer comma 1. Beer in itself is 1 count, so beer comma 1. River in itself is again a 1 count, so river comma 1. So we have key value pairs, that is deer comma 1, beer comma 1 and river comma 1. Similarly, when we come to the second line, we'll read each word from the line, that is car, and we'll mark 1 against it because it is 1 count in itself. So car comma 1, again car comma 1 and again river comma 1. What will happen with the third line? What will be the result of the mapping function when this is the input? It is exactly the same, that is deer 1, deer is in itself 1, car in itself is 1 and beer in itself is 1. Let's move on and let's go on to the shuffling phase. So let's see what happens in shuffling phase. In shuffling phase, for every key, there is a list prepared. Okay, so K2 comma list V2. For every key, there is a list of values that will be prepared in shuffling phase. So what shuffling phase will do is, so it will find the appearance of key bear and it will add the values into the list. So let's see what is happening. You can see that there are two incoming arrows. The first arrow is coming from list 1, so bear, and then in the list it has added 1. The other arrow was coming from this list, so bear comma 1 again. So what it did, instead of adding another key, it just added the value 1 in the list of values part. Okay, so the result would be bear comma list 1 comma 1 because there were two occurrences of bear in two different lists. Similarly, when I talk about car, so again for car, another list will be prepared for values. So as you can see that there are three incoming arrows. Two arrows are coming from the same list, so car 1 comma 1, and the third arrow is coming from the last list, again comma 1. Okay, so since there were three occurrences of car, hence the list of values will have three ones, 1 comma 1 comma 1. Okay, similarly goes with deer. Now deer was there in the first list and the third list, hence there were two occurrences, so deer comma 1 and 1. 1 and 1 is nothing but the values that are against the respective keys in the map phase, right? Can you tell me what will be the fourth answer? The answer would be river 1 comma 1. It is because river was found in two different lists. The first list, river 1, so first occurrence, and then river 2, so river, and then the list of values, that is 1 comma 1. Now comes the reducing phase. In reducing phase, what we are doing is we start aggregation of the values that were present in the list against every key. So for beer, there were two values present in the list, 1 comma 1, so the summation of these values will be done, so beer comma 2. Similarly for car, the values will be summed, so 1 plus 1 plus 1 becomes 3. A result from reducing function would be car 3. For deer, it becomes 1 plus 1, deer 2. What will be the last answer? The answer would be river comma 2. It's because the values are 1 and 1 and 1 plus 1 becomes 2. So this will be the result for river, and at last the final result will be sent back to the client with beer comma 2, car comma 3, deer comma 2 and river comma 2. This is how the entire word count process works when you are using map reduce way. Okay. Now let's execute this program practically. Okay, I showed you the entire process. Now let's execute this program, execute a word count program over the same input file that we saw and see what is the result. Okay, So I'll enter the password. This is the Edureka virtual machine that you can download from your LMS. I'm sure that the setup is already ready on your end. In case you're not ready with the setup, guys, please do that. Okay. So this is the input file that I have already created to save time. So this was the input in the example, right? Deer, bear, river, car, river, deer, car, bear. Okay. So what we are trying to do is execute a word count program over this. For your information, let me tell you that. So there are a set of MapReduce example that already comes with the Hadoop package that you download. Okay. So let me just show you. Even word count example is also a part of it. So I'll just take you there. My Hadoop is installed in user lib Hadoop. Let us see the contents of this folder. The MapReduce examples jar is present in the share folder. I'll just change the directory share Hadoop, and we need to go to the MapReduce part. We'll find the jar in this. This is the jar that I'm talking about, that is Hadoop MapReduce examples jar. Let me show you the examples that are present in this jar first. So Hadoop jar, Hadoop MapReduce examples 2.2.0.jar. So I'll execute this command. It will give me the list of all the classes, all the examples that are there within this jar. As you can see, one is aggregate word count, aggregate word list, BBP, along with a description. So you guys can go through it and try all the examples. What we are going to try is the word count example, a MapReduce program that counts the words in the input files. Okay, so this is what we are going to execute now. You can try other examples as well. As you have already seen the list of examples that is present in the Hadoop examples jar, now it's time we execute the word count example. But before that, we need to move the input file to HDFS first, and then only we can execute the MapReduce example. It is because MapReduce takes the input from the HDFS and dumps the output to the HDFS. Okay. So very first thing is I'll move the file. So Hadoop DFS, that is Hadoop Distributed File System, hyphen put, that is I'm trying to put a file into HDFS. I'll give the path of my file that is present on my local file system, that is home, Edureka, desktop, and then the name of the file input, and then I'll give the HDFS directory, that is I would like to store on the root directory of HDFS. Okay, I'll press enter. I'm sure by now you would be very clear with the HDFS commands. In case you are not, I request you to please execute the HDFS commands that are present in the HDFS tutorial blog, or you also have a document in the LMS. Okay, so looks like a file has been copied to HDFS folder. Let me just check if it has been done. So Hadoop DFS, I'll directly cat, that is I'll read the file directly, and I'll put the name of the file, that is input. So I'm telling that go look for the file input that is present in the root directory of HDFS and read it. Okay. So this was the file that we copied, right? Good. So let's execute the word count example. I'll write Hadoop jar, and I'll mention the name of the jar, that is Hadoop MapReduce examples jar. I'll mention the class that I want to execute, that is word count. I'll give the input part of HDFS, that is \input, and then I'll mention the output directory, that is first example out, and I'll press enter. So looks like it has started the execution. It is again connecting to resource manager. It is because the client submits the job to the resource manager, right? Good. As you can see, the map and reduce task has started now. First, the map task would be executed. You can also track the status of your job at this particular location. Okay. So for every job, there's an ID, application ID that is generated. So you can always go to port 8088, which is nothing but resource manager's port. Now, as you can see, the map has finished 100%, and finally the reduce phase would be executed. So reduce phase is also complete now. Now finally the job has executed successfully. Okay, as you can see, completed successfully. Let's go and check the output. Okay, I'll clear the screen. So Hadoop DFS -ls, and the name of the directory was first example out, and enter. As you can see, there is a success file that has been created and a part file. The output is always present in the part files. Okay. So we'll just read the part file now. Instead of ls, now I'll use the command cat, and I'll copy this part and I'll paste at the end of first example output. Okay. And let's press enter. This is the command that I'm using to read the final part file, the output. So this is the output: beer 2, car 3, deer 2 and river 2. Let's try and compare this with the input file itself. So first we'll read the input file, Hadoop dfs-cat \input, right? So this is the input file, and now we'll read the output file again, the part file. Now guys, can you compare? Is the result correct? Let's check. Beer, it says it has come twice. So beer 1 and then beer 2, right? Car has come thrice. So car 1, 2 and 3. Deer has come twice. So deer 1 and then second. Finally river came twice. So river 1 and river 2. So we can see that the output that has been given by the word count example is absolutely correct. Now, do you want me to execute the same word count example on a bigger file? Will that be interesting? Let me just show you. So for that, what I'll do is, let's open the browser first. Let's select a website like Apache Hadoop itself. Okay. So let's open Apache Hadoop. Apache Hadoop. So we'll open this website. So as you can see, there are multiple tags and multiple words there. Let me open the source file of this page. So I'll go to view page source. So how about running the MapReduce program on this page source and find out the frequency of every word that is coming in this page? Will that be something you would like to see? Good. So what I've done is I've written a small Python script. Okay, I'll just show you. Using that Python script, I'm trying to scrape the page that we have just opened, that is Apache Hadoop org. Okay, so I'll just change my directory to desktop first. I'll clear the screen. So the name of the script is scrape.py. Since it is a Python script, its extension is scrape.py. I'll open the file scrape.py. So in this, just I'm telling that this is where my Python is located. I'm importing a library that is called URL lib2. The page that I would like to scrape is http hadoop.apache.org that I have already shown you now. Using this command, that is URL lib2.url open Hadoop page, I am able to fetch the entire source code of this page in one variable that is called page, and then finally I am writing this page variable, the content of this page variable, in a file that is called Hadoop Apache. Okay, that will be created on the desktop. Okay, very simple script. I'll just save the file and I'll execute the script by /scrape.py. So you'll see that there will be a file that will get created once this script is finished. So right here, as you can see, Hadoop Apache is the file that has been created. I can open it for you. So it has the entire source code that was there in the Apache's website, right? Interesting. Now what I'll do is I'll execute the same word count example, but before that I need to move the file into Hadoop HDFS, right? I hope you remember. So I'll do Hadoop DFS -put. I'll give the path of this file, that is Hadoop Apache, the local path, and then I'll mention /, that is I would like to move this file to the root directory of Hadoop. Okay, I'll make the terminal full screen now. Now the file has been copied. Now I'll execute the word count example on this. So Hadoop jar, I need to give the entire path where my jar is located, that is user lib Hadoop, within that share folder Hadoop MapReduce, and then there will be the Hadoop MapReduce example jar. Next, I need to mention the class I would like to execute, that is word count. Now I'll mention the name of the input file that is present on HDFS, that is Hadoop Apache, and I'll give the name of the output directory where I would like to store the final result of this MapReduce program, and I'll name it as second example out. Okay, and let's press enter. As you can see, it's connecting to resource manager again. It is because it is somebody who executes all your jobs that are submitted from the client. So the MapReduce task has started now, as you can see. Which will be the first phase that will get executed, guys? Is it map or reduce? It will be map itself. I hope everyone is very clear that map will get executed first. So as you can see, map has executed now. Even the reduce phase is also over, as you can see. And we have the results written on HDFS. I'll clear the screen. So let's check the results quickly. So Hadoop DFS -ls, the output directory was second example out. And we'll find the part files within it, which will have the final output. So as you can see, this is the part file. Let's try and cat it. Okay, so Hadoop DFS -cat. I need to mention the entire path. I'll copy this and paste and enter. It will be a huge file. It is because the number of words that were present in the file was more than the previous input that we gave, right? As you can see, for every character, every word that was there in the file, you have the word count, right? So let me just clear this. So let's try and find out the count for Hadoop. Okay, so I'll simply execute a Linux command, that is grep Hadoop. On the output that will be received from after reading the file, I'll simply look for the word Hadoop. So Hadoop came into so many words, as you can see right here. So this is the command that I executed, and here is the result. Okay. So since this was the source code, it is a little messy. However, when you're working with real data set, you'll be cleaning that data set first, and then only you'll be executing your final processing. Okay. Even for cleaning, you'll be writing a MapReduce program. Okay. So how did you like the example? Matthew already says that, wow, that's a great example to observe. It gives the taste of real-time scenario. Okay, so Matthew, it was not a very real-time thing. However, still we were able to scrape a page and then do a word count on this. Okay, there are a lot of other things that can be done using MapReduce because the limits of MapReduce is endless. Okay, let's go back to our slides now. Now let's understand how MapReduce is using yarn to execute the jobs over the cluster. But before we go ahead, what does yarn stand for? Yet another resource negotiator. It is the one which allocates the resources for various jobs that needs to be executed over the Hadoop cluster. It was introduced in Hadoop 2.0 itself. Till Hadoop 1.0, MapReduce was the only framework or only processing unit that can execute over the Hadoop cluster. However, in Hadoop 2.0, yarn was introduced, using which we were able to go beyond MapReduce as well, as you can see in this slide. Okay, so we have HDFS in the bottom. In between, we have got yarn, and using yarn, a lot of frameworks are able to connect and utilize HDFS. Okay, so now even MapReduce has to connect using yarn request for resources, and then only it can execute the job over HDFS, that is Hadoop cluster. Okay, similarly, Spark can connect, other search engines can connect to HDFS, Storm can connect to it, HBase, which is a NoSQL database, which can connect to it. So the applications of HDFS became huge just because yarn was able to open the gates for other frameworks, other big data analytics tools as well. Let's move on. Let's talk about the daemons present in Hadoop 2.x cluster, which runs the components, that is storage and processing. And let's understand how does resource manager and node manager works in Hadoop 2.x cluster and manages the processing and the jobs that needs to be executed over the Hadoop cluster. Okay. So what is resource manager? Resource manager is the master daemon that runs on the master machine, which is a high-end machine. Node manager, on the other hand, is the daemon that runs on the slave machines or the data nodes, okay, along with the data node process, right? Let's understand this in a little more detail and explore other components as well, okay? So what is a client? A client is nothing but which submits a MapReduce job, like we did from the CLI, okay, that is command line interface. So it is also a client using which we were able to submit the MapReduce job. Okay, so it is a client. Similarly, a client could be a Java application or anything. Now, what is a resource manager? Resource manager, as I said, is the master daemon to which all the jobs are submitted from the client. It is the one which allocates all the cluster level resources for executing a particular job. Resource manager runs on a machine which is actually a high-end machine with good configuration, because it is the master machine which has to manage everything over the cluster. Okay. What is node manager? Node manager is a slave daemon that runs on the slave machines or the data nodes. So every slave machine will have a node manager running. It monitors the resources of a particular data node. Resource manager manages the cluster resources and node manager manages the data node resources. Okay. So what is job history server? It is someone who keeps a track of all the jobs that has been executed over the cluster or has been submitted on the cluster. It keeps the track of their status as well. Okay. It also keeps the log files of every execution happened over the Hadoop cluster. Okay. So what is application master? Application master is again a process that is executed on a node machine, on a slave machine, and created by a resource manager to execute and manage a job. It is the one which negotiates the resources from the resource manager and finally coordinates with the node manager to execute the task. Okay. Similarly, what is a container? A container is created by the node manager itself, which has been allocated by resource manager, and within the container, all the jobs are finally executed. Okay. Let me give you a pictorial representation of this process. So yarn application workflow in MapReduce. So as I said, resource manager. So there is a resource manager to which all the jobs are submitted. There is a cluster in which there are slave machines. On every slave machine, there is a node manager running. Okay. Resource manager has got two components. One is scheduler, another one is application manager. Okay. So Matthew says, what is the difference between application master and application manager? Application manager is a component of resource manager which ensures that every task is executed and an application master is created for it. Application master, on the other hand, is somebody who executes the task and requests for all the resources that are required to execute it. Okay. Now, let's say a job is submitted to the resource manager. As soon as the job is submitted, the scheduler schedules the job. Once the scheduler schedules the job to be executed, application manager will create a container in one of the data nodes. Now within this container, application master will be started. This application master will then register with the resource manager and request for a container to execute the task. Okay. Now, as soon as the container is allocated, application master will now connect with the node manager and request to launch the container. So as you can see, application master got allocated these two data nodes. Now this application master requested the node manager to launch these containers. Okay. As soon as the containers were launched, application master executed the task within the container and the result was sent back to the client. Let's understand this in a little sequential manner. Okay. So on the right, as you can see, these are the lines. The first one is the client. The second one is the resource manager. Third one is the node manager, and the fourth one is the application master. So let's see how are the steps executed between them. Okay. So very first step is client submits the job to the resource manager, as you can see right here. Now the second step is resource manager allocates a container to start the application master on the slave machines, right? The third step is application master registers with the resource manager, as you can see right here. As soon as it registers, it requests for the containers to execute the task. That is the fourth step. After that, application master notifies the node manager on which the container needs to be launched. Once the node manager has launched the containers, application master will execute the code within these containers. Finally, the client contacts the resource manager or the application master to monitor application status. Okay. And at the end, finally the application master unregisters itself from the resource manager and the result is given back to the client, right? So this is one simple sequential flow of how a MapReduce program is executed using Yarn framework.
Let me take this opportunity to explain you what is Yarn and how it works. We'll first start with Hadoop version 1, where we had MapReduce version 1. So in MRV1, the two core services were HDFS, that is Hadoop Distributed File System, and MapReduce, which forms the basis of almost all Hadoop functionality. All other components are built around these services and must use MapReduce to run Hadoop jobs. While MapReduce method enables user to focus on the problem at hand rather than the underlying processing mechanism, they do limit some of the problem domains that can run in Hadoop framework. So now let us know how MapReduce version 1 works in order to understand its limitations. The MapReduce processing model consists of two separate steps. The first step is parallel map phase, in which input data is split into discrete chunks that can be processed independently. The second phase is the reduce phase, in which the output of map phase is aggregated to produce the desired result. This is simple and fairly restricted nature of programming model, which lends itself to a very efficient and extremely large scale implementation across thousands of low cost commodity servers. When MapReduce is paired with a distributed file system such as HDFS, which can provide high aggregate I/O bandwidth, the economic of the system becomes extremely compelling. This is a key factor in the popularity of Hadoop. One of the key to Hadoop performance is the lack of data motion, such as compute tasks are moved to the server on which the data resides and not the other way around. Specifically, the map task can be scheduled on the same physical nodes on which data resides in HDFS, which exposes the underlying storage layout across the cluster. This design significantly reduces the network input-output patterns and keeps most of the I/O on local disk or on a neighboring server within the same server rack. To understand the new yarn process flow, it is helpful to review the original Apache Hadoop MapReduce design. As a part of Apache Software Foundation, MapReduce has evolved and improved as an open source project. MapReduce project itself can be broken down into the end user MapReduce APIs for programming the desired MapReduce applications, the MapReduce runtime, which is the implementation of various phases such as map phase, sort, shuffle or merge aggregations, and the reduce phase, and the MapReduce framework, which is the backend infrastructure required to run users' MapReduce application, manage cluster resources, and schedule thousands of concurrent jobs, among other things. This separation of concerns has high significant benefits, particularly for end users, where they can completely focus on their applications via the API and let the combination of MapReduce runtime and the framework deal with the complex details such as resource management, fault tolerance, and scheduling. As you can see in the right hand side image, the master process is the job tracker, which serves as the clearinghouse for all MapReduce jobs in the cluster. Each node has a task tracker process that manages tasks on the individual node. The task tracker are controlled by the job trackers. The job tracker is responsible for resource management, tracking resource consumption, availability, and job lifecycle management like scheduling individual tasks of the job, tracking progress, providing fault tolerance for tasks, etc. The task tracker has simple responsibilities like launch or tear down tasks on order from job tracker and provide task status information to the job tracker periodically. Hadoop MapReduce framework has exhibited some growing pains, in particular with regard to the job tracker, several aspects including scalability, cluster utilization, ability to control upgrades to the stack, and support for workloads other than MapReduce itself. MapReduce is great for many applications, but not everything. Other programming model better serves requirements such as graph processing and iterative modeling using message passing interface. As is often the case, much of the enterprise data is already available in Hadoop HDFS, and having multiple paths for processing is critical and clearly necessity. Furthermore, given the MapReduce is essentially for batch processing, support for real-time and near real-time processing has become an important issue for the user base. A more robust computing environment within Hadoop will enable organizations to see an increased return on their Hadoop investment by lowering their operational cost. Now, the first challenge was scalability. The processing power available in data center continues to increase rapidly. Consider the additional hardware capability offered by a commodity server over a 3-year period. In 2009, we had 8 cores, 16 GB of RAM, and 4 into 1 TB of disk. Coming down to 2012, we had 16 plus cores, 72 GB of RAM, and 12 into 3 TB of hard disk. These new servers are often available at the same price. In general, servers are twice as capable today as they were 2 or 3 years ago. MapReduce is known to scale to production deployment of approximately 5,000 server nodes in 2009 vintage. Thus, for same price, the number of CPU cores, amount of RAM, and local storage available to the user will put continued pressure on the scalability of new Apache Hadoop installations. So the next point is utilization. So in the current system, the job tracker views the cluster as composed of nodes with distinct map slots and reduce slots, which are not fungible. Utilization issues occurs because of map slots might be full while reduced slots are empty or a vice versa scenario. Improving the situation is necessary to ensure the entire system could be used to its maximum capacity for high utilization and applying resources when needed. Next is user agility. In a real-time deployment, Hadoop is very commonly offered as shared multi-tenant system. As a result, changes to Hadoop software stack affects a large cross-section of enterprise. Against the backdrop, users are very keen to control upgrades to the software stack, as such upgrades have a direct impact on their applications. Now let us discuss a problem that Yahoo faced. Yahoo was the first company to embrace Hadoop in a big way, and it was a trendsetter within the Hadoop ecosystem. In late 2012, it struggled to handle iterative and stream processing system of data on Hadoop infrastructure due to MapReduce limitations. Scalability bottleneck was caused by having a single job tracker. According to Yahoo, the practical limit of such design are reached up to a cluster of 5,000 nodes and 40,000 tasks running concurrently. After implementing Yarn in first quarter of 2013, Yahoo installed more than 30,000 production nodes on Spark for iterative streaming, Storm for stream processing, Hadoop for batch processing, etc. Such a solution was possible only after Yarn was introduced and multiple processing frameworks were implemented. So to address these needs, the Yarn project was started by Apache Hadoop community to give Hadoop the ability to run non-MapReduce jobs within the Hadoop framework. Yarn provides a generic resource management framework for implementing Hadoop applications. In Hadoop version 2.x, MapReduce has undergone a complete renovation. Yarn is also known as MRV2, that is MapReduce version 2. Yarn provides both full compatibility with existing MapReduce application and a new support for virtually any distributed application. The introduction of Yarn does not change the ability of Hadoop to run MapReduce jobs. It does, however, position MapReduce as a merely one of the application frameworks within Hadoop, which works the same way as it did in MRV1. The new capability offered by Yarn is to use the new non-MapReduce frameworks that adds many new features to the Hadoop ecosystem. So as you can see here, in Hadoop 1.x, MapReduce serves two purposes, that is processing paradigm as well as resource management. Now in Hadoop 2.x, Yarn takes all the responsibilities of resource management, or MapReduce or other frameworks can be used as processing paradigms. The fundamental idea of Yarn is to split the two major responsibilities of job tracker, that is resource management and job scheduling or monitoring, into separate daemons, a global resource manager and a per application master. The resource manager and per node slave, the node manager, forms the new and generic operating system for managing applications in a distributed manner. Yarn relies on these three main components for all its functionalities. The first component is the resource manager, which is the arbitrator of the cluster resources. It has two parts, a pluggable scheduler and an application manager that manages user jobs on the cluster. The second component is the per node node manager, which manages user jobs and workflow on the given node. The central resource manager and the collection of node manager creates a unified computational infrastructure of the cluster. The third component is the application master, a user job lifecycle manager. The application master is where the user application resides. Together, these three components provide a very scalable, flexible, and efficient environment to run virtually any type of large-scale data processing jobs. So, the resource manager is the ultimate authority that arbitrates division of resources among all the applications in the system. Per application master is a framework specific entity and is tasked with negotiating for resources from the resource manager and is working with the node manager to execute and monitor the component tasks. The resource manager has a pluggable scheduler component which is responsible for allocating resources to various running applications like capacity, queue, and other factors. The scheduler is a pure scheduler in the sense that it performs no monitoring or tracking of status for the application, offering no guarantees on restarting tasks that are not carried due to either hardware failure or could be application failure. The scheduler performs its scheduling function based on the resource requirement of an application by using the abstract notion of resource container, which incorporates resource dimensions like memory, CPU, disk, and network. The node manager is the per machine slave which is responsible for launching the application containers, monitoring their resources like CPU, memory, disk, network, and reporting the same to the resource manager. The per application master is responsible for negotiating appropriate resource containers from the schedulers, tracking their status, and monitoring the progress. From the system perspective, the application master runs a normal container. One of the crucial implementation details of MapReduce within the new Yarn system is the reuse of existing MapReduce framework without any major surgery. This step was very important to ensure compatibility of existing MapReduce applications and users. Now, the major benefits of Yarn is increased scalability, better memory utilization with containers, and the third one is other frameworks can be integrated like Spark, Storm, Hive, etc. Now, by adding new functionalities, Yarn brings new components into Apache Hadoop workflow. These components provides finer grained control for the end user and simultaneously offer more advanced capabilities to Hadoop ecosystem. Let's look at them one by one. So first is Resource Manager. As mentioned earlier, the Yarn Resource Manager is primarily a pure scheduler. It is strictly limited to arbitrating requests for available resources in the system made by competing applications. It optimizes the cluster utilization like keep all resource in use all the time against various constraints such as capacity guarantees, fairness, and SLAs. To allow for different policy constraints, the resource manager has a pluggable scheduler that enables different algorithms such as those focusing on capacity and fair scheduling to be used as necessary. So as we discussed, resource manager has two components, that is scheduler and application manager. So the scheduler is responsible for allocating resources to applications and does not offer guarantees about restarting failed tasks. Scheduler also have pluggable policies, that is capacity scheduler or a fair scheduler, etc. Moving down to application manager. Application manager is responsible for accepting job submission, negotiating with the first container for executing the application specific application master, and it also provides the service for restarting the application master on failure. Next is Node Manager. The Node Manager is Yarn's per node worker agent taking care of individual compute nodes in Hadoop cluster. Its duties include keeping up to date with Resource Manager, overseeing application containers lifecycle management, monitoring resource uses like memory, CPU, network, etc. of individual containers, tracking node health, log management, and auxiliary services that may be exploited by different Yarn applications. On startup, the node manager registers with the resource manager. It then sends heartbeat with its status and waits for the instruction. Its primary goal is to manage application containers assigned to it by the resource manager. Yarn containers are described by a container launch context, that is CLC. This record includes a map of environment variables, dependencies stored in remote accessible storage, security tokens, payload for node manager services, and the command necessary to create the process. After validating the authenticity of the container lease, the node manager configures the environment for the container, including initializing its monitoring subsystem with a resource constraint specified application. The node manager also kills container as directed by the resource manager. Now, next is application master. So application master is an important concept in Yarn. The application master is in effect an instance of the framework specific library and is responsible for negotiating resources from the resource manager. It is also working with the node manager to execute and monitor the containers and their resource consumption. It has the responsibility of negotiating for appropriate resource containers from the resource manager, tracking their status and monitoring progress. The application master is the process that coordinates an application's execution in the cluster. Each application has its own application master, which is tasked with negotiating resources from resource manager and with the node manager to execute and monitor the task. In Yarn design, MapReduce is just one application framework. This design permits building and deploying distributed applications using other frameworks. Once the application master is started, it will periodically send heartbeats to resource manager to affirm its health and to update the record of its resource demands. After building a model of its requirement, the application master encodes its preferences and constraints in a heartbeat message to the resource manager. In response to subsequent heartbeats, the application master will receive a lease on container bounds to allocation of resources at the particular node in the cluster. Depending on the containers it received from the resource manager, the application master may update its execution plan to accommodate the excess or lack of resource. Container allocation or deallocation can take place in dynamic fashions as an application progresses. The application master design enables Yarn to offer some important features like scalability. The application master provides much of the job-oriented functionality to the job tracker. so that the entire system can scale more dramatically. Simulations have shown that jobs may scale to 10,000 node clusters composed of modern hardware without any significant issue. As a pure scheduler, the resource manager does not have to provide fault tolerance of resources across the cluster. By shifting fault tolerance to application master instance, control becomes local rather than global. Second is moving all the application framework specific code into the application master generalizes the system so that it can now support multiple frameworks such as MPI, that is message passing interfaces, and graph processing. In reality, every application has its own instance of an application master. However, it is completely feasible to implement an application master to manage a set of applications. Furthermore, this concept has been stressed to manage long-running services which manage their own applications. Example, launching HBase in Yarn via a special HBase app master. So you can go ahead and see the responsibilities of application master, that is managing the application lifecycle, making dynamic adjustment to resource consumptions, managing execution flow, managing faults, providing status and metrics to the resource manager, interacting with node manager as well as resource manager, and so on. So next component is containers. Yarn has a pluggable scheduling component. Depending on the use case and user needs, administrator may select either a simple, that is first in first out capacity, or a fair share scheduler. The scheduler class is set in yarn default.xml file. At the fundamental level, a container is a collection of physical resources such as RAM, CPU, cores, and disk on a single node. There can be multiple containers on a single node. Every node in the system is considered to be composed of multiple containers of minimum size of memory and CPU. The application master can request any container so as to occupy a multiple of minimum size. A container is supervised by the node manager and scheduled by the resource manager. Each application starts out as an application master, which is itself a container, often referred as container 0. Once started, the application master must negotiate with the resource manager for more containers. Container requests can take place in a dynamic fashion at runtime. For instance, a MapReduce job may request a certain amount of mapper containers. As they finish their task, it may release them and request more reducer containers to be started. Now, as we have already discussed, yarn containers are described by a container launch context, that is CLC. So, this record includes a map of environment variables, dependencies stored in remotely accessible storage, security tokens, payload for node managed services, and the command necessary to create the process. So, a CLC includes everything that you need to launch a container. Moving ahead, let us understand the yarn workflow. So in earlier Hadoop versions, each node in the cluster was statically assigned the capability of running a predefined number of map slots and a predefined number of reduce slots. The slots could not be shared between maps and reduces. The static allocation of the slot wasn't optimal because slot requirements vary during the MapReduce application lifecycle. Typically, there is a demand of map slots when the job starts, as opposed to the need of reduced slots towards the end of the job. The resource allocation model in Yarn addresses the inefficiencies of static allocation by providing a greater flexibility. As discussed previously, resources are requested in form of containers, where each container has a number of non-static attributes. Yarn currently has attribute support for memory and CPU. The generalized attribute model can also support things like bandwidth or GPUs. So first, let's look at the client resource request. So as you can see, a Yarn application starts with a client resource request. A client communicates with the application manager component of the resource manager to initiate this process. The client must first notify the resource manager that it wants to submit an application. The resource manager responds with an application ID and information about the capabilities of the cluster that will aid the client in requesting resources. Next, the client responds with an application submission context. The application submission context contains the application ID, user, queue, and other information needed to start the application master. In addition, a CLC, that is container launch context, is sent to the resource manager. As we already have discussed about CLC, that it contains job files, security tokens, resource requirements, and other information needed to launch an application master on the node. Once the application has been submitted, the client can also request the resource manager kill the application or provide status report about the application. When the resource manager receives the application submission context from a client, it schedules an available container for the application master. If there are no applicable containers, the request must wait. If a suitable container can be found, then the resource manager contacts the appropriate node manager and start the application master. As part of this step, the application master RPC port and tracking URL for monitoring the application status will be established, using which your client can see the application status. In response to the registration request, the application master will send information about the minimum and maximum capabilities of the cluster. At this point, the application master must decide how to use the capabilities that are currently available. Based on the available capabilities reported from the resource manager, the application master will request the number of containers. The request can be very specific, including containers with multiple of resource minimum values. The resource manager will respond as best as possible to the request with container resources that are assigned to the application master. As the job progresses, heartbeat and process information is sent from the application master to the resource manager. Within these heartbeats, it is possible for the application master to request and release containers. When the job finishes, the application master sends the finish message to the resource manager and exits. Next is application master and container communication. At this point, the resource manager has handed off control of assigned node managers to the application master. The application master will independently contact its assigned node managers and provide them the container launch context that includes environment variables, dependencies located in remote storage, security tokens, and commands needed to start the actual process. Next, the node manager launches the container. When the container starts, all data files, executables, and necessary dependencies are copied to local storage on the node. Dependencies can potentially be shared between containers running the application. Once all containers have started, their status can be checked by the application master. The resource manager is absent from the application progress and is free to schedule and monitor other resources. The resource manager can direct the node manager to kill containers. Expected kill events can happen when the application master informs the resource manager of its completion, or the resource manager needs nodes for other applications. When a container is killed, the node manager cleans up the local working directory. When a job is finished, the application master informs the resource manager that the job is completed successfully. The resource manager then informs node manager to aggregate logs and clean up container specific files. The node manager are also instructed to kill any remaining containers, including the application master, if they have not already exited. Now let us quickly move ahead and look at the summary of the Yarn application workflow. So first, client submits an application to the resource manager. Then resource manager allocates the container and starts the application master. Then application master registers the container with resource manager. Second, the application master asks for the containers from resource manager. Moving ahead, application master notifies node manager to launch containers. Application code is executed in containers. Then client contacts resource manager and application master to monitor the application health. At last, application master unregisters with the resource manager and leaves all the resources acquired by it. So let us now quickly understand how Yarn works. Let's go to VM. So this is our VM. I'll be executing a simple word count example. So let us go to our Hadoop home. In share, Hadoop MapReduce. So we have a sample Hadoop MapReduce examples. So in this jar, we have a word count file which we can execute and check the status of Yarn. But before that, I'll show you the HDFS. So this is the HDFS. You can see we have one data node. Let us browse the file system. So this is the word count underscore input.txt file, which I'll be giving as input for the word count. If you are not having any file on your HDFS, you can go ahead and execute put command. So let us quickly go ahead and execute this command. The command is Hadoop jar, then the name of the jar file, that is Hadoop MapReduce examples. The name of the class is word count, and then we'll give the input file, that is, let me tally it, word count underscore input.txt, and the output files will be stored in output directory, which is in the root of HDFS. So let us quickly go ahead and execute this command. Meanwhile, we'll go to our Yarn web UI, that is 8088. So this is the Yarn web UI. As you can see, this is the application that we are executing. This is the application ID, the user, so the name of the application, that is word count, type of application. Again, the status is accepted, final status is undefined. There is one container running, allocated CPU vcores is 1. And here you can track the progress of the application. This is the tracking UI. Let us go to the tracking UI. So state is succeeded. Let us go back to our terminal. As you can see, the program has been successfully executed. You can also see the parameters over there, like number of bytes to be read, number of bytes to be written, number of read operations, the number of write operations. Again, you can figure out the MapReduce framework, how many number of map input records, number of map output records. And then we have all the MapReduce details over here. So let's not worry about them. So it gives you all the details related to that job which you have executed. You can see the log files that has been created while executing this job. You can also track it on your web history server, that is localhost 19888. So again, you can see this word count job, and you can again track the details, that average map time, shuffle time, average reduce time. So these are the details, guys. Let us go to that HTTPS browser and look at the output file that has been created. So this is the output file. Let's go ahead and download it. So as you can see, the number of count for car is 4, deer is 3, and the river is 2. So this is the output that we received. I've given a simple input file. Let me show you the file as well. This is the input which we have given, and this is the output which we have received.
So what were the problems associated with the relational database system? As I have already mentioned that for a Hadoop developer, actual game starts after the data is being loaded in HDFS, and the developers play around this data in order to gain various insights that are hidden in the data stored in HDFS. So, for this analysis, the data residing in the RDBMS needs to be transferred to HDFS. And you all know that the task of writing MapReduce code for importing and exporting the data from relational database to HDFS is tedious. So this is where Apache Scoop comes to rescue and remove the pain of data ingestion. So why do we need Scoop? It's a known fact that before big data came into existence, the entire data was stored in relational database servers in the relational database structure. But with the advancement of Scoop, it makes the life of developers easier by providing CLI for importing and exporting the data. And Scoop internally converts a command into MapReduce tasks, which are then executed over HDFS. It uses Yarn framework to import and export the data, which provides fault tolerance on top of parallelism. It also uses Yarn framework to import and export the data, which provides fault tolerance on top of parallelism. Not only that, it is also very useful for data analysis, high in performance, and provides command line interface. Now let's understand what is Scoop. So before I tell you what is Scoop, let me tell you how the name Scoop came into existence. By now, I hope that you have got an idea that it is used for data transfer between relational database and HDFS. So before I tell you what is Scoop, let me first tell you how the name came into existence. The first two letters in Scoop stands for the first two letters in SQL, and the last three letters in Scoop refers to the last three letters in Hadoop, that is OOP. So it clearly depicts that it is SQL to Hadoop and Hadoop to SQL. That is how the name of Scoop came into existence. So what is Scoop? It is a tool used for data transfer between RDBMS like MySQL, Oracle, SQL, etc. and Hadoop like Hive, HDFS, HBase, etc. It is used to import the data from RDBMS to Hadoop and export the data from Hadoop to RDBMS. Simple. Again, Scoop is one of the top projects by Apache Software Foundation and works brilliantly with relational databases such as Teradata, Netezza, Oracle, MySQL, etc. It also uses MapReduce mechanism for its operations like import and export work and work on a parallel mechanism as well as fault tolerance. As I have already mentioned that it provides command line interface for importing and exporting the data, the developers just have to provide the basic information like database authentication, source, destination, operations, etc. And the rest of the work will be done by Scoop tool itself. Sounds much reliable, correct? Now let's move further and talk about some of the amazing features of Scoop for big data developers. First, full load. Apache Scoop can load whole table by a single command. You can also load all the tables from a database using a single command. Next, incremental load. Scoop provides the facility of incremental load where you can load the parts of a table wherever it is updated. Next, parallel import and export. Again, as already mentioned, Scoop uses Yarn framework to import and export the data, which provides fault tolerance on top of parallelism. Next, compression. You can compress your data by using gzip algorithm with compress argument or by specifying compression codec argument. Next, Kerberos security integration. So what is Kerberos? It's a computer network authentication protocol which works on the basis of tickets to allow the nodes that are communicating over a non-secure network to prove their identity to one another in a secure manner. Next, load data directly into Hive and HBase. Here it is very simple. You can load the data directly to Apache Hive for analysis, and you can also dump your data in HBase, which is a NoSQL database. Now let's see what's next. The architecture is one of the empowering Apache Scoop with its benefits. Now, as we know the features of Apache Scoop, let's move ahead and try to understand Apache Scoop's architecture and its working. So when we submit our job or a command through Scoop, it is mapped into map task, which brings the chunks of data from HDFS. And these chunks are exported to a structured data destination. And combining all these exported chunks of data, we receive the whole data at the destination, which in most of the cases is RDBMS server. Next, reduce phase is required in case of aggregations, but Apache Scoop just imports and exports the data. It does not perform any aggregations. Map job launch multiple mappers depending on the number defined by the user. For Scoop import, each mapper task will be assigned with the part of data that is to be imported, and Scoop distributes the input data among all the mappers equally in order to achieve high performance. Then, each mapper creates a connection with the database using JDBC and fetches the part of the data assigned by the Scoop, and then writes that data to HDFS, Hive, or HBase based on the arguments provided in the command line interface. So this is how Scoop import and export works. Like they gather the metadata, again, it submits only map job. The reduce phase will never occur here, and then it stores the data in HDFS storage. Coming to Scoop export, it's the same thing. The data will be reversed back to RDBMS. So here, the Scoop import tool will import each table of the RDBMS in Hadoop, and each row of the table will be considered as a record in the HDFS. And all the records are stored as text data in the text files or binary data in sequence files. On the other hand, the Scoop export tool will export the Hadoop files back to the RDBMS tables. Again, the records in the HDFS files will be the rows of a table, and those are read and passed into a set of records and delimited with the user-specified delimiter. So this is all about the Scoop architecture and its import and export. Now, let's execute some Scoop commands and understand how it works. So at the first, we have Scoop import. That is, it imports the data from RDBMS in Hadoop. The command goes very simple. Here, you have to just provide the connection for MySQL, your IP address, your database name, your table name, the username for MySQL user. If you have set privileges for password, you can specify the password or it is not required, and the target directory. Now, let's see how to execute. So I'll open my terminal and check whether all my Hadoop daemons are up and running or not. So I can see that all my Hadoop daemons are up and running. So now let's execute Scoop help and see whether the Scoop has been properly installed or not. So these are the available commands in Scoop. Here I will show you the execution and explain you few of these commands. Now this is also properly been set. Now I will open another terminal and connect to MySQL database. The command goes like this. My user is Edureka, so I'm giving it as Edureka. You can give it as root if your user is root. Simple. So now I'm into MySQL database. If you want to create a database, you can create a database by giving this command, create database, database name, etc. As I have already created a database, so I'll just specify show databases command to list the database present in the MySQL database. So now these are the list of database present here. So now I want to use employees database. So I'll give use employees. Database got changed. Now I want to list the tables present in the employees database. So I'll give show tables. So these are the 11 tables present in the database employees. Now let's say I want to use employees table. So what will I do? I'll just give select star from employees. That is table name. So it's just a huge amount of data that is present in this database. So there are these many rows present in this table. Now open the other terminal where you have executed this command, and here I will show you how to import the data present in that table to HDFS. So how we are going to do that? By using scope import command. The command goes like this. The IP here is localhost, and you know that employees is my database name, and the username will be Edureka, and the table that I have chosen is employees. So I have not set any privileges for password, so I'm not specifying the password over here. So it got executed, and you can see the number of job counters, the MapReduce framework, the input records, output records, etc. So what happens after executing this command? The map task will be executed at the backend. Now let's check the web UI of HDFS. That is, the web UI port for HDFS is